All right, so I forgot that this does that. It kicks me off after 20 minutes, so I have to post this as two different ones. I think I found a workaround. I gotta get it squared away. I just forgot about it. So the idea here, just to refresh what happened, you have a strain of 0.003 in compression. When you move the concrete like that, right, if you squish it down a little bit, you get a uniform distribution of concrete stresses over the length of or over the width of the column, right? Its magnitude is 0.85 F prime C, kind of like the Whitney stress block. It's not exactly the same, but it's pretty close. That's how I like to think about it, right? And then each of these bars, right? This row of bars. Well, actually, I guess I lied to you earlier. This is looking at it this way, right? Because I've got three rows of bars: three row bar, a row bar, and a row bar, which correspond to this bar, and this bar. So this is looking this way. These guys are looking this way on the column. Okay, and you have three rows of bars. I should have made them wider. And so, anyways, you stress it to 0.003. You then get these stresses from the steel, and then you get this stress from your concrete, and then from that you could calculate the force from the steel row one, force from the steel row two, and the force from the steel row three, and then what the concrete compression force is. Okay, and then you add them up. The one thing we have to talk about really quick is what are these stresses right here: FS1, FS2, and FS3. And if you recall, right, how our steel behaves is it goes up like this, right, and then it goes across like that, and then really it goes through a straight hardening, right, but we assume that it just keeps going, that it always caps out at Fy, right, and where this happens, by the way, where this thing yields, that's about 0.002. Okay, that for a 60 ksi steel, that's where that yield stress begins, is at a strain of 0.002. If you look up here, and by the way, this behavior right here, right, works for compression and tension, right? We're talking compression right here. So if we've stressed this thing out to 0.003, that means it's gone up right here, and that 0.002 it yields, and then so 0.003 is over here someplace. Okay, which means that our steel has yielded. Just from the very beginning, our steel has yielded. And so we could substitute this in the equation above. Just say, well, Fs1 is equal to Fs2, which is equal to Fs3, which is equal to Fy. Right? It's all yielded. Right? You don't have to check strains and stuff like that. We just know that the steel has yielded because it's been stressed to 0.003. Just by definition, we're pushing this thing until when the concrete crushes, which is at 0.003. Okay, so in our derivation of our equation, we then look at equilibrium, right? And we can kind of plug in what each of these components are, right? I could also say, well, let me do that right here. This is C sub C. C sub C. This is equal to 0.85 F prime C times Ag minus area steel, the total area steel, right? So it's just taking this, stress right here, right, and then multiplying it by the area over which it acts, and the area at which it acts is over this whole area. That's the gross area, is the whole area of the concrete, which is B times H, right, and then you subtract out how much steel is the total area steel, all of these pieces of rebar. You subtract out those components right there. And so that's what that equation is up above. So let's just keep going with this. Right, we're almost done with this little derivation here. So you have to sum of the forces have to be equal to 0, right? If not, this thing is accelerating. That's something that we should avoid with our structures, is having them accelerate, right? And so we're going to look at the applied load P naught, the load that we're going to apply to the top of the structure, how much load we can apply to it. That's going to be equal to CS1 plus CS2 plus CS3 plus C sub C, right? So you just take all of these forces, add them up, right? Each of these forces, add them up, and then they'll end up equaling the P that's applied to it. And I guess I should probably put that P on here. This would be your applied moment, or sorry, applied axial load. This would be P. Right? And so this thing has to be in equilibrium. So these forces that are internal, they have to add up to this external force P right here. Okay? And so that's what this is doing right here. Right? The sum of the forces are equal to 0, so those have to be that. CS1 is equal to AS1 times Fy. CS2 is equal to AS2 times Fy. And CS3 is equal to AS3 times Fy. So obviously this can be simplified a little bit. We can talk about the total amount of steel compression force. That's equal to the sum of all of these CS's, right? Which is, we can lump these things, AS1 plus AS2 plus AS3 times Fy. And this is what we're going to call AS total, which we already jumped ahead a little bit on this. That's the total amount of steel. Sum them all up. All right. And so then we already mentioned what CC was. CC is equal to 0.85 F prime C times BH. That's the area, gross area, minus the area steel. Make that clear. This is AG. It'd be slightly different for a circular column, right? AG would be pi d squared over 4. Okay, but anyways, if you take these things, and plug them in, right, or simplify it, take those things and plug them in up above here, right? You take this and put it in up there, and this and put it up in there, and what you get is this equation down here. You get that guy, right? And so, right, you take the total compression force that a column can take, a concentrically loaded short column can take, is is the total area steel times Fy, right? It makes sense that you'd have that. And then times 0.85 F prime C, that's the magnitude of the stress block, times the area that the concrete, times the area of concrete, the total area of concrete. It's the gross area minus the amount of area that the steel takes up. And that's your total capacity. Pretty straightforward, right? Especially compared to what we had to do for columns for calculating the capacity. This is close to, this isn't it yet, right? This is close to PN in ACI. It's not quite what the nominal capacity of a column is in ACI. There's some modifications to that equation, but it's pretty dang close. This is one of those cases where they actually give you an equation in ACI. I think I will drink there. Anyways, it's really close to the equation that shows up in ACI. And we'll obviously look at the equation that shows up in ACI in a few minutes. Right? So that's where we stand right now. So that's how we calculate the capacity of a concentrically loaded short column. I guess the other thing to at least mention is this idea of axial load and bending, right? It turns out most of your columns will have some combination of axial load and bending, right? There's just a very few that have just concentrically loaded. That's all we're going to deal with in our class is the concentrically loaded columns, but I'm at least going to talk to you about axial load and bending a little bit. And just so show you kind of how you would go about designing these things. We won't actually have to do it in this class, but it's worth mentioning. So and talking about what the effect that it would have. So this would be a case where you would have axial load and bending, right? If you remember back to structures 1, right? If you apply loads on this thing like this, you'd end up with a deflected shape that would go. Those are straight lines are on. Right. That's what your deflected shape would be with those applied loads. And so these columns right here, these columns would have bending induced by this lateral load and axial load induced by these guys. And actually these guys actually cause a little bit of bending on it too, right? When it's in the offset position, there is a little bit of moment applied from that as well. And so that's one case that you'd have axial load and bending. Another place you'd have axial load and bending is if you had an eccentrically loaded column, right? So this is just if you had a column and you had this load was offset, right? Here's the center line right here, right? And that is like an eccentricity. I think typically that's referred to as an E. And so if you have both of those things, you end up with a column with axial load and bending, okay? And so both of these things, I'm going to talk about both of these cases. You have axial load and bending. Oh, my straight lines are not on this time, right? You end up with a loading condition that looks like this, right? You have a moment, or another way to look at this is you have a moment and an axial load, right? You have a concentric axial load and then an eccentric moment, or sorry, a moment and a axial load. And you kind of can treat those things as being separate, right? Is that they both, using superposition, they both cause effects on it. One's bending and one's an axial load, right? And you remember that from statics, right? This could be interpreted as just that could be interpreted as a point load and a combination of a moment. And same thing with these guys, can do the same thing. And so if we look at the stresses really quick on what an axial load and a moment would do, if we look specifically at axial load stress, right, these stresses would simply be this, right? Just what we saw before. Actually, when we did the derivation a few minutes ago, this is what those stresses would look like, right? But if you look at the bending component, right, the bending stresses would do this. Right, so this is bending stresses. Okay. And you add them together, you would have a behavior that would look like this. And so you wouldn't have, right, you end up with this case where you don't really have any tension in this. I think that I'd be able to draw straight lines, but it would be wrong. Yep. Okay. And so you don't have any bending stresses, right? Or sorry, tension stresses, right? Because when you add these two things together, you have this compression stress, and now that you got tension on one side and you got compression on the other side, what you end up when you add the two together, I guess I didn't show that this plus this equals this. What you end up with is no tension on this side. You just end up with less compression and more compression on that side. Less compression on this side, more compression on this side. And so anyways, obviously this behavior, right, where you have that type of behavior, it's not going to be the same mechanics for calculating its capacity. It's close, to be honest, right? The mechanics that we had for bending and the mechanics we had for axial load are pretty close to each other. And the procedure that we had, where you lay out the strains, then you look at the stresses, and then you apply then you look at the forces and you apply equilibrium. When you do more complicated columns, when you have an axial load and bending, it's the same process. It just ends up being a little bit more difficult because you have to do a little bit of iteration in the process, in the procedure. There's a little bit of iteration that has to happen, and so it's a little bit more complicated than just simply deriving an equation. It ends up being an iterative solution, and so that's beyond the scope of this class. That'll be something that you would cover in concrete, I'm assuming. Okay. But I did want to just at least point that out to you. But then what you could do, and actually people do this, and you can look up these charts if you wanted, and if you're actually going to do a design, you would use one of these charts, is this idea of a PM interaction diagram. So on this axis, we're going to put the axial load P, and on this one, we're going to put the moment M. Okay, and so if you were to plot the axial load, or I guess the capacity of the beam, as a function of the moment that's applied to it, you would get a curve that looks like this. Right? And so this is what they call a PM interaction diagram. And you can use this thing for design. And I didn't draw that quite right. Let me just have it come right there. All right, there we go. That's a better one. And so this right here, this point right here is going to be P naught. When we calculated P naught before, right? These mechanics up here for P naught, right, is this case on the far left right here. Right? Because in that particular case, you have no moment and straight axial load, right? And so that's what P naught is. This point right here, right, is Mn, right? Mn is what we did for the first part of this class, right? This is a beam without any axial load, right? And so they both start in those places, which makes sense that it would go from that place to the other place, okay? And so kind of, and this point right here actually is the balance failure. This is where epsilon sub s is equal to epsilon sub y. That's where the balance failure. Oh no, that's wrong. That's not really. It's so I have in my notes, but that's not right. That's where balance failure is when epsilon sub s is equal to 0.003, right? That would mean that no. What is it? Oh, you think, what is it? Concrete crushes at the same time. Oh yeah, that's what it is. Epsilon sub c is equal to 0.003, and epsilon sub s is equal to epsilon sub y. Actually, what I wrote there was what I had originally written was correct. Okay, so in this particular case, the concrete crushes right at this point. Okay, right where the concrete crushes, the steel yields at that exact same time. That's the balance point. And I always like to think about this as being here. You would have this is a beam with axial load, right? And then up here we have a column with moment, right? And so that's kind of I always like to think of that. Up in that region, you have a column that has a little bit of moment applied to it. Down in this region right here, you have a beam with a little bit of axial load. And if you have a beam and you apply axial load to it, it actually increases its capacity, right? It moves to the right here, which indicates that its capacity is going up. But if you have a column and you apply a moment to it, you decrease your capacity. It actually goes down, right? The other thing that gets applied in this is the whole phi factors, right? And the phi factors are part of this as well, and they change with how much ductility you have. It turns out that these guys, the phi factors would go like something like this, and there's a little bit of a kink in it. I'm gonna do that again. Right. So this is phi PN and phi MN. When you apply the phi factors to it as well, you back off of that axial load capacity and the moment capacity when you apply the phi factors. And so you end up with curves like this, okay? And so these curves, so you could do this for all different, you'd have a curve like this for each beam design, okay? So again, these are the PM interaction diagrams. You'd have one of these PM interaction diagrams for all different types of beams that you would have, right? And they have charts that have a whole bunch of these things superimposed on top of each other. And the way you use these things for design is you plot. Let me write this down. Oh, I can type it. I don't know why I'm typing it. It doesn't actually help much. Plot MU and PU on graph. If you're inside curve, you're okay. If you're outside curve, you're not. Okay. All right. And so what you would do is you come in and say, all right, I'm going to plot, kind of thing. Plot this guy, right? This would be a plot of PU, comma, MU, right? In that particular case, we're okay, right? Because we're inside of this curve. We're inside of that curve, so you're okay. If you plotted it out here, PU and MU, right? And you're outside of there, you are no good, right? Because you're outside of that curve. And you can imagine a whole bunch of these things plotted on the same thing, right? And they all correspond to a different type of column design. You come in and you plot, you got all these things floating around, and then you plot like this guy right here, and then you read up and to the right, and the one that's the first one to contain your stuff, that would be the column design that you would use. So these things are very common in design, a very simplified way of doing it, right? It's beyond the scope of this class, besides just knowing that it exists, a little foreshadowing for the future, right? On what you might expect in the next class, or go on to be a real engineer. You might see these PM interaction diagrams, and you could say, "Yeah, I've seen those before," right? And then I know that I plot my demand and my demand, and I check it to see if I'm inside of one of these curves. This kink right here, I drew it with a little kink. This has to do with our phi factors, which we're going to talk about in a few minutes. They change with how much ductility you have in your beam, right? It's the same phi factors that we use for beam design, right? With the phi, how it changes between 0.65 and 0.9, right? When they change like that, that happens with columns as well. They look like this. They go, right? Remember this? That's what our phi factors did. They went like that, depending on how much strain you had down in the bottom, right? There was some 0. Look, I can keep writing 0.9, right? And so it was that. That still applies for column design, right? And so that kink is when it changes between here and here. That's this kink right here. Okay. Anyways, you've seen it. You know that it exists. We're going to stick to this type of behavior, though. I wanted to point that out, that there's other behavior exists. Now, ACI requirements. There's a lot of stuff related to the ACI requirements. Okay, what do they specifically say? That's a good question. I don't want to talk about this. So, one, I want to say this. I want to say, to look at the. Let me see, what do I got there? The strength. All right. You could say ACI, packet, included, D2L. Add it, okay. So I did the same thing that I did for beams. I made a little document, or I kind of plucked out all the relevant sections for columns, spread out all over the place. Okay, but I plucked them out, and then you might look at that as we move forward. I'm going to pull out the key components of it here in a second, but you might do it. So chapter 10 gives us the general. Chapter 10. It's general requirements, I guess. General requirements. Okay. Chapter 22.4 it deals with the strength, and then 25.7 spiral and tie requirements. Okay. And so just like with shear design, right? Shear design, not only did you have to design for strength, there was also minimum spacing requirements for your ties and stuff like that. Those still, well, what's going on here? There's something similar for columns as well. We have to talk about the spiral and tie requirements. But in the next couple of sections, and we go through these notes, I'm going to talk about the strength design and these requirements. But I would look at this packet just to see some of the wording associated with column design. And so for design for strength, Okay, like I said before, our PN equation is very similar to what we derived before, right? This is what we derived. This part right here is what we derived in our notes above, right? 0.85 F prime C times AG minus the area of steel plus the area of steel times Fy. So that shows up directly in the code, okay? But we got these two other components here. Phi, recognizable, right? That obviously there's going to be a strength reduction factor, but this alpha is something that is new. We haven't discussed yet. So let's talk about what that is for, right? So alpha is equal to 0.85, I guess it's 0.8 for ties, is equal to 0.85 for spirals. And to get a little bit of reward there for using ties versus spirals. There's another reward down in our phi factors as well, but what these guys are for are to account for accidental eccentricities. Okay, even though you've designed your column to be concentric, right? We're going to say, yep, I'm going to load this thing up. Right? My goal is I'm going to load this thing up, or my design says, yep, I'm going to take this thing and I'm going to put the load right smack dab in the middle. If it's not right in the middle and it accidentally, oh, I don't know the whole thing, it accidentally is over to the right a little bit, right? That your capacity would go down, right? You're designing it as if it's perfectly concentric, but what happens if the load's off a little bit, right? Do you think that happens in design quite a bit? Or during construction? Absolutely, right? You have it very idealized on how this thing is going to be constructed, but if for some reason it ends up being offset just a little bit, your capacity will not be as much as what you thought it was going to be, right? You'd think that would be covered with your phi factors and stuff like that, but I guess it's so much of a problem. ACI is like, listen, you gotta put in this extra factor to account for this accidental eccentricity, and then to show what it does. That's another one of the other reasons why I talk about the PM interaction diagrams, right? There's what your actual behavior is going to be, but if you accidentally put a moment on it, right, that'd be moving to the right on this graph. If I accidentally put a moment on it, right, notice what's happening. This thing is diving down. That's why I redrew it earlier. This thing's diving down, and so if you accidentally put an eccentricity on it, you actually are getting capped off right here, right? Your capacity goes down when you when you have accidental eccentricity, right? Because adding a moment to an axial load reduces your capacity, okay? And so I would say, just a little note, right? Alpha is someplace out here, right? The alpha, just to remind yourself that alpha is there to account for the fact that you lose capacity when you move to the right. I say it counts. Uh-oh. Alpha accounts for this, right? The fact that it goes down a little bit. Okay, so that's what alpha is doing. Oh, okay, yep. And so then what about the phi factor, okay? The phi factor is the same phi factor as beams. Right? Same as beams. Right? So this should not be new to you, right? So this is what the phi factor is, okay? It starts out dependent, right? So I guess just to refresh your memory on these phi factors, I kind of mentioned it up above, why that kink shows up in the PM interaction diagram. But this thing is, right, for a tied column, it starts out at 0.65, and then once you get to a point where your steel yields, you start getting more and more ductile behavior, and so it increases, okay, and then about 2.5 times the yield capacity at 0.005, you start getting rewarded with a phi factor of 0.9. And then Spiral is a little bit different, right? It starts out at 0.75 and then it ramps up to 0.9, right? And that causes that kink up above. But that's the same, we use the same exact graph for column design, okay? With column, concentrically loaded short columns, these are tensile strains. These things are loaded up in compression, only compression. If you look back at our capacity derivation of above, we assumed that they're all in a compression of 0.003 for a concentrically loaded short column. They're all at 0.003. Since they're at 0.003 in compression, they actually aren't even on this graph. They're over here, right? Over to the left here is where columns end up being. I'll make that red so it stands out. Say over here, right? And so what does that tell us? It just tells us that for a tied column, right? For a tied column, the phi is 0.65, and for a spiral column, the phi is 0.75, right? That's all it says, because we're columns are over to the left there, right? And so, when we did these things for beams, there was this point right here where it was like, right, that this was like 0.004. And there was a requirement that your concrete had to reach your steel had to go to at least 0.004 before, but at least 0.004 when you're designing a beam without axial load, right? And you may have been asking yourself at the time, well, why the hell do you even have the rest of the graph? Why do I even have this graph if you're not even allowed to design in that area? Well, you are allowed to design in that area when you have axial load. And this is one of those cases we have axial load. And so if you have something with axial load and bending, right, you're somewhere in this spectrum right here, right? And then, if you go all the way in this curve, that phi factor goes all the way from here all the way up and up to 0.9. And so you actually trace out that whole thing when you do the full PM interaction diagram. Anyways, enough about that. So that is what ACI says about strength, right? You just have to make sure that your PU, right? I guess we can write that here, that this has to be greater than or equal to PU, right? Our factored axial load demand has to be less than the capacity, right? And then there's the capacity equation, and that's the capacity equation, right? We'll talk about a design procedure in a little bit. This is really easy to do just for calculating the capacity, right? Super easy, and you can just do a quick check on it. But how do you do design of a reinforced concrete column? That's the subject of a couple pages down. Okay, the other requirement that ACI has, like we mentioned before, slabs have very, we start out with slabs and beams, and shear design, you start out like, I'm going to design this thing for strength. And then I have to make sure that I meet these minimum spacing requirements and longitudinal reinforcement requirements and all this other stuff. So strength requirements are simply this. As long as you meet this requirement, you're okay. But then you also have to meet these other requirements, okay? So there's also a minimum amount of longitudinal steel you have to include, okay? And you may be asking yourself, why? Okay. Why do I have a minimum amount of reinforcement that I have to include? And so let's actually talk about that. This is straight out of the code, okay? Right? If this thing is just concentrically loaded, short concrete column, right? There should be no tension in it anywhere, and so you should just be able to not include any longitudinal reinforcement. But the code says you have to use a little bit of reinforcement. Required to ensure a behavior. Okay? I think that's specifically what the code says about why that minimum is there. Why do you have a minimum amount of reinforcement required? And the code says, well, it's to ensure reinforced concrete behavior, right? To account for any, we'll say and I'm going to add this part, and to account for any accidental Okay, I would say that, right? You have to include just a little bit of reinforcement. Just what happens if you've designed it as a concentrically loaded short column, but what if there's like an earthquake or something like that, and you get a little bit of tension on one side that you weren't expecting, right? Having some reinforcement in there is crucial for that. And so the ACI code is aware of this, and they say, yep, you absolutely have to use a minimum amount of reinforcement. The maximum max is to limit congestion. Okay. Limit the amount of congestion you're going to get inside there. If you put too many, right, bars may not fit, right? That's the problem. If you put too much steel in there, then it might not fit in the beam itself, right? And they're saying, yep, so there's this range of the amount of steel that you can include in your beam, okay? And if we haven't talked about what those limits are, here the limits are 10.6 reinforcement limits, okay? The maximum and the minimum maximum longitudinal reinforcement. So this is the longitudinal reinforcement, by the way. You know, I think I maybe mentioned that before. There's a minimum amount of longitudinal reinforcement you have to include. Now, the allowable so what is it for non-pre-stressed columns, which we have, and for pre-stressed columns with average of FPE, the 225 psi, which doesn't apply to this, right? We don't have a pre-stressed member. Areas of longitudinal reinforcement shall be at least 0.01 AG, but shall not exceed 0.08 AG. So they say you have to be within that range, right? And so if you're talking this thing, right? So what specifically this thing says, as it says that 0.01 AG, our total area steel, AG. Okay. That's, I left the 1 out of there. 0.0. 0.01. No, I did not. What did I do? 0.1. What am I doing here? Okay, that's what it has to say. The amount of steel you have has to be in between those ranges right there. Okay, another way to write it is in terms of reinforcement ratios, where you take the area steel divided by AG. So you could say 0.01 has to be less than rho is less than 0.08. And this would be called rho G, right? Where rho G is equal to area steel divided by AG. Okay. That's another way of writing the same thing. You can either talk about in terms of minimum reinforcement ratios, or you could talk about it in terms of minimum amount of steel. So they say you have to be within that range. So that's one limit. When you're doing your design, you have to make sure you're within those limits right there. Okay? And then the next thing was the minimum number of longitudinal bars that are required, right? And this one kind of makes sense as well. You have a minimum amount of steel, but then you also have a minimum number of bars. And what does that say? Well, it says that for non-pre-stressed columns, which we have, columns with the average of which we got, the minimum number of longitudinal bars be A, B, or C. 3 within triangular ties. I've never seen 3 triangle ties, but I've never seen triangular ties, but it has to have 3 if you have triangular ties, 4 within rectangular ties, and a minimum of 6 if you have a spiral reinforced column, right? And so it's just saying, it makes sense that you have, if you've got a column that's doing this, you have to have at least 4 bars. You have to have 1 in each corner, right? The other thing I should say is your columns have to be they have to be what's the word I'm looking for? Symmetric. They have to be symmetric. You can't come in, so you can't come in and put, like, I want to put 4 bars on one side and no bars on the other side, right? You can't come in and say, I'm going to put I'm gonna put five. This design needs 5 bars. So I'm gonna put 1 bar here, 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 and here. Right? You can't do that. The other thing you can't do is put it in the middle. Right? And the reason you can't put it in the middle is part of this thing. The reason you're including this reinforcement is to help with any accidental moments or something. If you put this reinforcement in the middle, that's not going to help you with with accidental moments. And so you have to have at least 4 for rectangular. For spirals, you have to have at least 6 around in a circle. Right? So for a spiral, you have to have at least 6. 1, 2, 3, 4, 5, 6. Right? You have to have at least 6 of those in there. And then for triangles, you have to have 3. Right? Which I don't think you're going to run into much in your careers. But just in case you do, you heard it here first. You got to have at least 3. Okay, so that's the longitudinal reinforcement. When you're picking longitudinal reinforcement, you just got to make sure you're within those limits, and you have to make sure that you're within those limits. And you have to use the minimum number of reinforcing bars. Okay, so then we come on to tie requirements, right? Ties are super easy to design. It's very prescriptive. Remember, these ties are confining the core. They're also being used for shear as well. So if you have axial load and bending, you're going to have some shear in there, and you have to design for that as well. So the tie requirements. Right? I've just copied the ACI section in here, right? The spacing of the ties, right? And what I mean by the spacing of the ties is if what we're designing, right? This is what they look like in the cross section. This is what they look like on the cross section. But what they look like, the spacing we're talking about. So here's the height of the column, right? This thing is applying the axial load like this, right? Is how far do we space these things? Okay, how do we far do we space them, and what size do they need to be? Right. So this would be what we're looking at is that spacing right there. Now, according to ACI, it says ties shall consist of a closed loop of deformed bar with spacing in coordinates with A, B, or C. It has to have a clear spacing of at least 4/3 the diameter of the aggregate, right? So they have to be the spacing between them. So this says clear spacing. So this is the distance between them. So if you're looking at 2 bars, right? So the bar, right? We're talking about this. What a great diagram. This will explain a couple things. This from center to center is the spacing, right? And then this, right? That's the clear spacing. Right? In between that reinforcement. So center to center spacing versus the clear spacing. So according to ACI, it says that the clear spacing, number 3, enclosing a smaller longitudinal, larger longitudinal bars bundled. Up here. Clear spacing has to be 4/3 the diameter aggregate. So your spacing has to be bigger than the diameter of the aggregate. Makes sense, right? You want to make sure your aggregate can fit in between those, the reinforcement, in between the spiral, or in this case, the ties. And then the center to center spacing shall not exceed 16 dB of the longitudinal bar, 48 dB of the tie bar, and the smallest dimension of the member. And so what you do, we'll do this in design here a little bit, but you just have to, you calculate this, and this, and the smallest one is the one that tells you how tightly these things have to be spaced. Yep, the least of these. So you calculate this, and then the least dimension, and then you pick the smallest, and that's what your spacing is going to be. Very prescriptive on how you go about designing it. The diameter of the tie bar shall be at least A or B. Number 3 for enclosing number 10 or smaller longitudinal bars. Number 4 for enclosing number 11 or larger longitudinal reinforcing bars. Okay, and so that's what they end up being. So again, very prescriptive, very straightforward. And then it says you can use wire as well. The other requirement is rectangular ties shall be arranged to satisfy A and B. A, every corner and alternate longitudinal bar shall have a lateral support provided by the corner of a tie with included angle of not more than 135 degrees. I wonder what he's saying there. Okay. No unsupported bar shall be farther than 6 inches clear on each side of a tie from the lateral supported bar. And so to describe that a little bit, they've provided these little diagrams up here, and you can study these a little bit. But the idea behind it is these guys would be considered tied, right? Because it's at a corner of a reinforcement. And so if you think about this thing wanting to buckle out, right? it can't buckle out because there's rebar and tension around it. Okay, right? This thing, it would want to go, it wants to buckle out this way. Well, this bar right here is resisting it. Okay, and then same thing on this side. If it wants to buckle out this way, it can't because this piece of rebar is loaded in tension and it can't. These bars right here, it may want to buckle out this way, but the only thing resisting it from buckling out this way is the fact that this guy is in bending, right? This would want to bend out a little bit, right? That's not considered being tied, right? Even though it's within that reinforcing, it doesn't really help it because a bar in bending is not the same as a bar in axial load. And so the requirements specifically say, that you have to, if these things are, you could read it down here, but if they're greater than 6 inches, they have to be tied. If they're less than 6 inches, then they don't have to be tied. The other requirement is that every other bar has to be tied, right? So in this case, you have these guys going across the bottom right here, and this would be okay because you have a spacing, right? These guys, so this guy's tied, this guy's not, this guy's tied, this guy's not, this guy's tied, right? And so this satisfies every other bar being tied. And they put in these things are called J hooks that go around here just to kind of help tie that reinforcement. The other thing they do is they sometimes put in this diamond reinforcement in the middle. So they have the external ties going around the outside, right? And then they also put in this little diamond guy to support these interior bars. And it might be that these guys are greater than 6 inches. Right? If this is greater than 6 inches, you have to support these ones. Even though it's every other, you still have to support them. And so the way they're doing it is putting in this diamond reinforcement in the middle. And so as long as this thing is less than 6 inches, these guys can go untied. If this is greater than 6 inches, you have to put in like a J hook or something like that. And so it's very prescriptive on how you go about designing this. And we'll do it in an example here in a few minutes. Or actually probably in the next lecture. This thing's going to be a really long lecture. My apologies. But then you could kind of break it up over a couple of days. So spiral requirements. No, this is a little bit more difficult. How long this thing is going on here? Let's see. 47 minutes. Yeah, I'm going to stop this. I'm going to stop this one here, and then I'm going to start off with spiral requirements, and then we'll do an example for the next lecture. Okay, and go through this design guide here in a little bit. So, anyways, stay tuned for more lectures, guys. I think these two went a little bit long, but the good news is you can fast forward me when you want, and you can pause me and skip certain components if you're tracking really well. So, like I said, let me know if there's any concerns or issues with watching these, and if you have any homework questions and things of that nature. So I think that I did get one homework question that I'm going to try to post a little video here in a few minutes on how to address that. Like I said, in a few minutes here, I should be able to get to that. So there's a homework posted, and